All right, so can we use Green's theorem to help us solve area problems? Interesting question. So we want to be able to compute the area of different things, and how can we use Green's theorem? Can we use Green's theorem? So let's recall that the area of a region D, now I'm not going to get into the details in this video, but I am assuming things about my region D. It has to be quote unquote nice. But I've got this region D, I want to compute its area, and we've learned before that you can take the double integral over your region D of 1 dA, and that's actually area. Double integrals of a function over a region in the xy plane gives you volume, but volume is area when the height is constant 1. And so let's think about it. If I want to switch this double integral back to a line integral, Green's theorem lets me do that. I'm going to scroll up to Green's theorem. Don't look at the screen if it's going to make you sick. Scroll up right here, and we've been going this way. We've been going from the line integral to the double integral, and it really has made life quite easy for us in the problems that we've looked at. It was significantly faster last time in the last example to just use Green's theorem. But what I want you to realize is this is equals. So you can go the other way too. We can start with a double integral, and we can go backwards to a line integral if we can get everything to set up right. So let's go ahead and scroll back down to our problem, our question that is, and have a look at this. So let's realize if we're going to switch to a line integral from a double integral using Green's theorem, then I need some vector field PQ where this 1 is Q partial x minus P partial y. That's what Green's theorem says. It says you can switch this integral, let's write it in a different color so that you know what this is. You can switch the line integral over f dot dr, where f is PQ, to, that's not what I wanted to do, this double integral, as long as what's right here is Q partial x minus P partial y. And so how do we do that? Well, we need an f, a vector field f, that satisfies Q partial x minus P partial y is 1. So I thought I'd give you several of them. So here's one. So you could consider the vector field f of xy equals 0x. Okay, now let's check. P partial y, this is P and this is Q. P partial y is 0 and minus P partial y minus Q partial x. And so P partial y is 0, Q partial x is, I've got it backwards, Q partial x minus P partial y. Q partial x is 1 minus P partial y is 0. So I do indeed get 1. Let's